So good morning. Let's start with the next topic, bilinear transformation method. In our last class, we have been discussing about impulse invariant method, and we have seen that even though the impulse invariant method, it allows us a linear relationship between the analog frequency and the digital frequency. However, it has got its own disadvantages. One of the disadvantage is what we discussed about was that there was many to one mapping. That means many of the analog frequency components, they were mapped into one point in the digital frequency. Okay, so this resulted in the aliasing. Okay, so this corresponds to aliasing, and that is undesirable. To overcome such undesirability, we discussed that there is a need for band limiting the signal before we can process the signal using the digital filter that has been designed using impulse invariant method. Okay, second thing, we have also discussed that the filters designed with impulse invariant method is mainly used to design the low pass filter. Not other types of filters can be designed comfortably. Now, what is the reason over here? The reason is that if you look into the Z plane, so this circle, unit circle, it is having a radius of imaginary Z. Is that when we are dealing with this impulse digital filters designed with the impulse invariant method, and when we look into the Z plane, so what happens is that if we go into the depth of the impulse invariant method, which we are not going into due to the shortage of time, so what happens is that there is another circle at the lower end. Okay, now this circle, it is having a center at 0.5, x equal to 0.5 and y equals to obviously 0. So you can say at 0 comma 0.5 we have the center. Okay, sorry, 0.50 xy now. 0.50, right? So also the radius of this circle is equal to 0.5. So we have a very small region, and within this small region only we can place the poles. Okay, now this is the reason why we can only develop low pass filter using the impulse invariant method. Okay, so other filters cannot be designed comfortably using the this low pass using this impulse invariance method. Okay, now as I was telling you, due to these disadvantages, there was a need for another transformation. Okay, now to overcome these disadvantages, the next transformation, bilinear transformation method, it was proposed. Okay, in this method, what it is said is that the S is replaced with 2 by capital T within bracket 1 minus Z inverse divided by 1 plus Z inverse. In the previous case, what we were having, In the previous case, we were having that 1 by s minus p1, it was being transformed into 1 by 1 minus e to the power pi t z inverse. Okay. So instead of this transformation matrix, in the bilinear transformation matrix, we will be using s equals to 2 by capital T 1 minus z inverse divided by 1 plus z inverse. Okay. So this is the transformation matrix. Now let us see. So relationship between the analog and the digital poles. Let us see that one. Okay. Now we start with the transformation matrix S equals to 2 by T 1 minus Z inverse divided by 1 plus Z inverse. So this gives us ST by 2, which is equals to 1 minus 1 by Z divided by 1 plus 1 by Z. So multiplying numerator and denominator with Z, we get Z minus 1 divided by Z plus 1. And if you solve this, you get ST into Z plus 1 divided by 2 is equal to Z minus 1. So st by 2z minus of z is equal to minus of st by 2 minus 1. So you see all the solving. After solving, we get to this equation, which is important. Z equals to 1 plus st by 2 divided by 1 minus st by 2. Okay. Now over here we know that s is equal to sigma plus j omega. Okay. Now over here, when we have the sigma plus j omega, we will put this into this equation, and from there we will find out the modulus of z. Now when we are having this modulus of z, so if we have, say, we again have the three conditions. We have the s plane, we have the z plane. Now we have to see the location of the poles, where the locations of the poles are being put. Okay. So what happens over here is that if you see sigma less than 0, so that means, say for example, over here we have this sigma. Let us take an example for our convenience. Say it is minus of 0.5. Okay. So in this condition, what will happen? This would be 1 minus something, and the denominator will be 1 plus something. So the denominator will be higher. So the modulus will be less than 1. So the left hand side plane, it is basically mapped within the unit circle. Okay. When sigma equals to 0, this is 0, this is 0. So 1 plus this thing, 1 plus this thing, both becomes 1. So the frequency axis, it maps onto the unit circle. And lastly, when sigma is greater than 0, we have modulus of z greater than 1. So it meets our all the criteria for designing a digital filter. Okay. Now once it is done, so let's see, most important thing is, what is the relationship between the analog frequency and the digital frequency. So in the previous case, we can see the relationship between analog and the digital filters. Whatever the transformation matrix it has been provided, it meets all the criteria for the placement of the poles to design a digital filter from the analog filter. Now, just like in our previous case in the impulse invariant method, where we discussed about the frequency relationship between the analog frequency and the digital frequency, here also we want to have the same thing. So again we start with the same thing, s equals to 2 by capital T 1 minus z inverse divided by 1 plus z inverse. Okay. Herein S plane is a big plane, Z plane is also a big plane. We are only interested in the frequency axis. So S will be replaced with j omega and Z will be replaced with e to the power j omega. So herein we will be basically moving onto the frequency axis, j omega axis, and with while we replace Z with e to the power j omega, we will be moving onto the unit circle, right? Now just place these values, okay, and solve it. What we get? We get an equation, omega equals to 2 tan inverse of sigma t by 2, which is again equivalent to omega analog frequency equals to 2 by t tan of omega by 2. Okay, so over here now what happens is that this our omega analog frequency, it varies from 0 to infinity. Okay, it varies from 0 to infinity. So when sigma is 0, when would be omega 0? At tan 0, if you see, if you put 0, then omega will be 0, right? When this thing, when it will be infinity, tan pi by 2. So if tan pi by 2 is infinity, then omega is pi. So when our analog frequency, it varies from 0 to infinity, that means our digital frequency, it will vary from 0 to pi. Similarly, if you go from minus infinity to 0 and minus pi to 0, same condition will apply. Now we will just concentrate at this moment in the same thing over here. So otherwise you can also look into this 4 quadrant of this thing. So over here what will happen, this only continues. This one is the mirror what you call relationship, it will follow over there. So if you have this pi over here, below you will be having the minus pi, like this. Okay. But for the sake of our understanding, we are just taking the first quadrant. Okay, so in the impulse invariant method, we are having omega equals to omega t. However, in this case, bilinear transformation method, we are having omega digital frequency equals to 2 of tan inverse of sigma t by 2. Okay, now the first case, if you see, it is a linear relationship. It is a linear relationship. Okay, on the contrary, when we are applying the this bilinear transformation method, this relationship, it comes out to be in this fashion. Okay, we are discussing that when we are having this we are applying this bilinear transformation method, if you see the frequency response, it shoots up linearly, and then towards the pi it is moving towards the pi. Okay, and at frequency tending to infinity, this digital frequency, it will be pi. Okay, so it is basically not going to the pi at a particular value, right? Now what is happening, the main advantage over here is that there is only one to one mapping. There is only one to one mapping. Okay, so it is a very good sign that we are having only one to one mapping, that each analog frequency will be mapped to a specific digital frequency. However, the problem here is that this one to one mapping, it is a non-linear mapping. In the previous case, in the impulse invariance method, we had a linear mapping. However, there was many to one mapping. To overcome that, when we designed this bilinear transformation method, the problem over here is that we are having one to one mapping, but that one to one mapping, it is a non-linear function. It is not a linear function. That means some of the frequency components will be widespread, and now some of the frequency spectrum or the components, they will be compressed within the frequency domain. So if you see, in this region where there is a what do you call you are having this uh, near the what you call linear region. Over here you are having you are maintaining a region, and if you see, there is a relationship between the linear relationship between the frequency components. Okay. However, as you go towards the higher frequency digital frequency components, these frequency components, they are getting compressed within the frequency axis. They are getting compressed within the frequency axis, and this phenomena of the compression of the frequency component within a small region of the digital domain, it is regarded as the frequency warping. It is regarded as the frequency warping. To understand this, let us take this example. This is this chart or the graph. Basically, this graph is very meaningful, but you need to understand what it is. So in the first, this graph, it is nothing but your omega t and omega relationship. Here what we are having, we are having this frequency relationship what we discussed. Okay, this bottom graph, we are having analog frequency and modulus of h of omega. Okay, when we design a filter using this method, we basically have a maximally flat response. So all the frequency response, see, it is having a particular value of a. We have just inverted it for our convenience. Now if I sample this frequency of having some certain width, okay, frequency response is linear. Okay, so over here also we are having this because both are analog frequency domain, so both are, see, the width, it will be same. Okay, now if we try to map this into the digital frequency, now you start seeing the fun. If you see this region width and this region width, both are similar. Here also it is nearly similar, but as we are going towards the high frequency component, it has significantly reduced. It has significantly reduced. Now if you look into the digital frequency versus its amplitude response, it is having a maximally flat response, same frequency value, say amplitude of a at this point. And if you look into the width of this sample frequency component, as we go towards the higher sample frequency component, we are having the lower width. That means the higher frequency components are getting compressed within a smaller region in the digital domain. Okay, so as I told you, while we designed the filter using the bilinear transformation method, we expect a maximally flat response. Okay, and secondly, we have seen that we are having a frequency distribution which is non-linear in nature. Now with this, let's take up a couple of examples. It's similar to the impulse invariance method, but still we have to look into the this thing as the transformation matrix is changing. So let us take this example. Hs equals to 2 by s plus 1 multiplied by s plus 2. Okay, so we have to transform this into a digital filter. So we have this transfer function, transformation equation. So we apply this transformation equation over here, just simply put it, and just after solving you get hz. Okay, and herein since t is not given, so t would be equal to 1 second. Okay. Next is h of Sn equals to 1 by Sn square plus 1.414 Sn plus 1. So it is basically Sn, it stands for normalized transfer function. Okay, normalized transfer function. So we have to do some what do you call, some minor adjustments into the equation for solving this kind of questions. Okay, so it is given that the cutoff frequency of the digital filter what we are expecting is 0.4 pi. Okay, yeah, right. So from here we see that the cutoff frequency, it is given by 0.4 pi radians per second because it's already given in our equation, and since capital T is given over here and the capital T is equal to 1 second. Okay. Now from here we have to find out the analog cutoff frequency because this h of s, it is dealing with the analog frequency component. Okay. So though we are given with the digital frequency component, we have to calculate the analog frequency component. Okay. Now what we have, 2 by t tan of omega c by 2 omega c is this thing. You just solve it and you get analog frequency 1.453 radians per second. Okay. Now to calculate Hs, we have to replace Sn by S by omega c. Okay. So Sn would be replaced with S by omega c. Just replace it, solve it, you get the Hs. Now from next there on onwards, the method is same. You use this transformation equation, put it in the place of S and solve the equation. That's it. Okay. So this is how the numericals needs to be done. In the previous cases, if you see the digital what do you call frequencies cutoffs, they have not been given. However, in this case, you have been given with digital frequencies. Okay, and also the normalized transfer function in the analog domain. So that's why you have to do this kind of trick to get the things done. If similar question comes for the impulse invariance method, again up to this point the method would be same, and then from here to here that only the transformation equation it will be changing. Okay. So with this we will be stopping today. So please solve these two questions. I'm going slow for these numericals because this needs consideration. If you don't practice it, it will be difficult. Any questions? Any doubts? You are not practicing. You have to do this in the class, yeah. I didn't get you. These are the only two previous two questions. You want the last classes questions? There is no question over here. No numericals over here. It's just the relationship between the analog and the digital poles. Because we are starting with this transformation, bilinear transformation equation. So from there, what is the relationship between the analog pole and the digital pole? We need to understand whether this equation is will be satisfying the digital filter designing criteria or not, because we are taking the equation of the analog filters and we are transforming it into the digital filters, right? So we need to understand whether that mapping, if you do the mapping, it would lead to a stable filter or not, if you are using a stable analog filter. And the next one is the relationship between the analog and the digital frequencies, because it is important. In our last class we discussed about the impulse invariant method, where there was a linear relationship between the digital and the analog filter, analog frequencies, but the problem over there was that there was many to one mapping. So many of the analog frequency components, they were mapped onto a single point in the digital domain. Okay, so these are just the basics to get your basics cleared. Okay, now these two are the equations. This type of numericals you can expect. What I told is that this kind of question you can also get in impulse invariance method, and if you get over there, the steps up to this point, it would be the same. Okay, then for finding out the hz, you have to apply the impulse invariant method transformation equation. Here you are using this equation, s equals to 2 by t multiplied by 1 minus z inverse by 1 plus z inverse. However, in uh, impulse invariance method, you will have to apply a different method, different equation.